Hey guys, so right now we'll be looking at question 2 of lecture 14, testing questions part B, which is about the Miquel theorem, Steiner-Miquel theorem. Basically, they're saying ABCD is a convex quadrilateral and the extension of AB, DC intersect at E, the extensions of AD, BC intersect at F. Prove that the four circumcircles of triangles BCE, CDF, ADE, ABF are concurrent at one point. So this might sound like a mouthful, but basically what we need to do is get to the whiteboard and start drawing things out to get a sense of what they're asking for. So in typical competitive programming fashion, we're going to be using Paint, and I'm gonna be putting the question up on the screen as an image on top. Let me just make it a tad bit bigger. Okay, so what we're gonna be doing is following the question. Okay, so how big is the canvas? Alright, this shall be sufficient. ABCD as a convex quadrilateral, right? So let's just draw as best as I can a convex quad. Let's just take this. Holy shit. Wait. Shaky hands, my bad. A bit too long, I see. Okay. Here, let's just trim it a bit. I'm just going off feeling. Okay. Maybe like this. And like this. Okay. So this is, I should call this A, B, C, D, right? So AB and DC intersect at E. So we're gonna be extending AB and DC and write out E. I'm just using my mouse to draw, so it's a bit wonky, my bad. AD and BC intersect at F, so we're gonna be doing this. At F. Wait, this part's a bit wonky too. I'll just make it a tad bit better. Oops. This is a real struggle, guys. Fuck it. Okay. A bit better. That's in a line. Okay, now to the actual question. Prove that the four circumcircles of triangles BCE, CDF, ADE, and ABF are concurrent at one point. So they're saying that these four circles, right? I'm just gonna quickly outline what four circles we're looking at. BCE, CDF. So CDF is something like this. ADE is something like this, and ABF something like this. So you're gonna look at this and be like, holy shit, what's going on? And yes, I get it. Basically, there are four circles, so you're not even supposed to consider all four at the same time, because it's gonna be just way too messy. Let us consider the first two circles that I give, which is BCE and CDF. Okay, so let's just draw the first two things that we need to meet. Like this. 天哪. Not the best at drawing. Okay, just take it as two perfect circles that are drawn here. So now we're considering circles B, CE, and DEF. Okay. So there are two more that we need to fulfill the criteria, which is ADE and ABF. Just write it down first, just so that we don't forget which circles we have or not have. Okay, so we need ADE and ABF. So basically what you're supposed to realize is these two circles, as you can see, they intersect at two different points. One at point C. I know the drawing doesn't look like it, but they're supposed to intersect exactly at point C because they both have D, not EF, sorry, DCF. The circles DCF. So because they both have the letter C in the name, they are concurrent at C, but also they are also concurrent at this point, another point, because they are circles, right? They can be concurrent at 2 points. Let's call it M, and notice that you can drop perpendiculars down. So let's drop a perpendicular down from M to DE or DC, whatever you call it. So basically this line along here, let's just drop a perpendicular down. I don't know where it's supposed to land, but just make it perpendicular, and let's call this Q. Now we drop perpendicular from M to, let's just drop it to BE, shall we? Let's call this P, and let's drop it also to BC and call it R. Okay, so considering this triangle CBE, since M is a point outside the triangle and has lines connected to each of the sides at 90-degree angle, we can call this thing has a theorem to it. I don't know what its name is called specifically now. Oh, Simpson's. You can go and search about it. It's called Simpson's line. And what it says that if there's a point like M outside the triangle and you drop perpendiculars to all its sides, the intersection with all the sides, so P, R, and Q, they are supposed to be collinear. So let me just use another color to represent collinear. I know that my drawing does not make it look like it's collinear at all, but let's just take it to be collinear. So R, P, Q are collinear. Sorry. Okay. Now, if we consider dropping one more perpendicular from M to AD, right? Let's just drop one more perpendicular and call this like, what letters have we not used? P, Q, R, S. Yeah, okay. So let's call this S. And if you consider now triangle C, D, and F. Consider triangle C, D, F, right? M is outside the triangle CDF and has perpendiculars dropped to the sides DF, CF at R. So DF is at S, CF at R, and DC at Q. DC extended, or I should say. So this is also a point outside the triangle CDF that has perpendiculars dropped to all three of its sides, S, R, and Q. So we can also conclude that S, R, and Q are collinear. So another line, S, R, and Q. So if you might notice, right, since R, P, and Q are collinear, and S, R, and Q are collinear, this just means that it forms a longer, just another longer collinear set of points, which is S, R, P, and Q are collinear. So yeah, and since this is collinear, right, it opens the door to another set of circles. So let's just try to remove the clutter. We just found that S, R, P, and Q are collinear. So let me just remove the blue circles that I drawn, because they are a bit distracting. Okay. Let's just remove this one, this one, okay. We can keep the perpendicular lines because we need it for the next part. Remember, we need to include these two triangles. So, okay, right now we also know that, obviously, since M is the intersection of the previous two blue circles that we drew, M is intersection of circumcircles of these two, 1 and 2. Now we just need to include the others, right? Okay, now let's consider circumcircle of ADE. ADE, okay. Boom. How do we prove that M lies on the circumcircle of ADE also? Well, we can notice that M, okay, let's just see ADE, this triangle. M has a perpendicular dropped to S, which is on one of the sides of ADE. So this side is checked off. ADE also has the sides DE, which also has a perpendicular drop at Q. So this side is checked off, and AE, this side, also has a perpendicular drop at P. So this side is checked off. So M, this point, has perpendiculars dropped to all three sides of triangle ADE. So by the Simpson's theorem, not only S, R, and Q are collinear, M is also on the circumcircle of ADE. This is also another thing that Simpson's theorem says. So this means that M on circumcircle of, let's just use this to denote circumcircle of ADE. I don't want to write too much with the mouse. So since M is intersection of these two circumcircles, and M is also on ADE, this third one, that means M is an intersection on all three so far. So we just need to rope in the last one. Now let's consider the circumcircle of ABF. Something like this. It doesn't even matter at all anymore. ABF, sorry. ABF. So how do we conclude that M is on circumcircle of ABF? Well, M has a perpendicular dropped to FA extended at S, right? So FA, this side is done, checked. M also has a perpendicular drop to FB extended at R. So this is checked off, and M also has a perpendicular drop to side AB extended at Q. Similarly, M is the Simpson's point of triangle ABF, and hence M lies on the second circle of ABF. So now we roped in the last one. M is on circumcircle of AD and also on circumcircle of ABF. So since M is on the circumcircle of all these 4 triangles, M is the intersection is the intersection point of all the 4 circumcircles of the 4 triangles that we have here, and hence we solved it. That's all for the proof. I didn't want to write too much because I'm on a mouse, but the entire proof can be written out in nicer words. So yeah, we're done with this problem.